Hello, so let's begin one more lecture session on infinite series. Now, in the last lecture session, we had seen alternating series, and today we will again see some series where we can have both positive and negative terms, and we will see two very important concepts of absolute and conditional convergence. So, let us see these topics one by one. Absolute convergence. An infinite series n equal to 1 to infinity un of real numbers is said to be absolutely convergent if the series n equal to 1 to infinity modulus un is convergent. That means we are taking modulus of each of the members of the given series. We may call that as an absolute series, and of course that is a positive series. And if that absolute series is convergent, then we say the original series is absolutely convergent. The next definition is for conditional convergence. An infinite series n equal to 1 to infinity un of real numbers is said to be conditionally convergent if the given series summation un is convergent but not absolutely convergent. So conditional convergence means that the given series is itself convergent, but its absolute series is not convergent. And we follow this with a very important theorem which says that if the series summation un of real numbers is absolutely convergent, then the series is convergent. So please remember this important result that if a series is absolutely convergent, that means if the absolute series is convergent, then the original series is also convergent. And this we can easily understand because of course the absolute series will be a bigger series. So if the bigger series is convergent, the smaller series, which can contain a mixture of positive and negative terms, is also going to be convergent. Now, with all these definitions and theorem, let us now begin to look into problems. So first we have here a problem on conditional convergence. Show that the series 1 minus half plus 1/3 minus 1/4 and so on converges conditionally. So what do we have to show then? We have to show that this series itself is convergent, but the absolute series of this is not going to be convergent. Now, we can see easily that this is an alternating series, so we can try the Leibniz theorem to test whether this is convergent or not, right? And this series, which we have already seen, it can be written in the form summation n equal to 1 to infinity minus 1 to the power n minus 1 un, where un is of course 1 by n. Now it's very obvious that this sequence un, that means 1 by n, is monotonically decreasing, and also limit un n tends to infinity will be 0 because un is nothing but 1 by n. Hence, easily by Leibniz theorem, we can now conclude that this series is convergent. However, now note what is the absolute series of this one. If all the terms are positive, that is nothing but summation 1 by n. And what is that? We all know that. That is nothing but the harmonic series, which is again known to be divergent. So therefore, what do we see? That the given series is convergent, but its absolute series is divergent. Hence, we can conclude that this series converges conditionally. Now, next example. Show that the series summation n equal to 1 to infinity cos nx by n square is absolutely convergent. Now, this one is of course containing a mixture of positive and negative terms because we know that cos nx can take both positive and negative values. And we have to check its absolute convergence, so we just start with taking a mod sign, looking into the absolute series. So first of all, we can write the series as summation n equal to 1 to infinity un, where your nth term un is cos nx by n square. So if we take a modulus sign, mod un will be mod cos nx by n square, and we all know that mod cos nx will be less or equal to 1. So this is less or equal to 1 by n square. And let us call this as Vn. Now notice that if we look into the series summation Vn, that means summation 1 by n square, that is nothing but a P series with P equal to 2, which is known to be convergent. And therefore now, by comparison test, we can conclude that this absolute series summation mod un is convergent, because what we see here that mod un is less or equal to Vn, and the bigger series is known to be convergent, hence the smaller series is also going to be convergent. So now, since the absolute series sigma mod un is convergent, we can finally conclude that the given series is absolutely convergent. One more problem, let us see. Test the convergence of the series x minus x squared by root 2 plus x cubed by root 3 minus x4 by root 4 and so on. Now observe one thing, this is a power series, and what kind of series it will be, it will depend on the value of x. If x is positive, then it is an alternating series, but if x is negative, then all the terms will be negative, isn't it? So we cannot directly now use the Leibniz theorem because it may not be always an alternating series. So let us try to check for its absolute convergence. And we know that if a series is absolutely convergent, it will be itself convergent. Okay, so now how can we write the series? The series may be written as summation n equal to 1 to infinity un, where un is minus 1 to the power n minus 1, x to the power n by root n. So if we look into mod un, this is mod x to the power n by root n, and therefore modulus of un plus 1 is mod x to the power n plus 1 divided by root n plus 1. So now if we want to apply the ratio test, because we are considering modulus of un, so that means we are considering positive series. So let us now try to find out limit n tends to infinity mod un plus 1 by un. So if we put here the expressions for un plus 1 and un, what do we get? You see that this is mod x n plus 1 and mod x n. So we will be left with mod x, and these two terms will give us root over n by n plus 1, which is otherwise 1 by 1 plus 1 by n. And now if we take the limit as n tends to infinity, 1 by n of course goes to 0. So the limit is mod x. So then what is your conclusion from the ratio test? The ratio test says now that this series will be convergent if mod x less than 1, divergent if mod x greater than 1. And of course we know that the ratio test is going to fail if mod x is equal to 1. That means for two values of x, x equal to plus 1 and minus 1. So these cases we have to now look separately. So let us see first the case x equal to 1, and if we put x equal to 1, we see that the series reduces to 1 minus 1 by root 2 plus 1 by root 3 minus 1 by root 4 and so on. So this is now an alternating series which is written in the form summation 1 to the power n minus 1, 1 by root n. So being an alternating series, we may now apply Leibniz theorem. And so what we observe, we can easily see that this sequence 1 by root n is of course monotonically decreasing, and limit n tends to infinity 1 by root n, this also tends to 0. So therefore by Leibniz theorem, the series summation minus 1 to the power n minus 1, 1 by root n is convergent, or otherwise our given series is convergent when x is equal to 1. And let us see the last case, what happens when x equal to minus 1. Now the series becomes minus over 1 plus 1 by root 2 plus 1 by root 3 plus 1 by root 4 and so on. So this is, we can write as minus sigma 1 by root n. And now observe that this sigma 1 by root n, this is nothing but a p series with p equal to half. And p series is known to be divergent for p less or equal to 1. So this is a divergent series summation 1 by root n, and therefore the given series minus summation 1 by root n is also going to be divergent. So therefore our final conclusion is the given series is convergent for minus 1 less than x less or equal to 1, because we have found here it is convergent for x equal to 1, and earlier by ratio test also we have seen that it was convergent in the range minus 1 to plus 1. So finally the given series is convergent for minus 1 less than x less or equal to 1. Okay, so with this we will close today's session, and this actually completes our syllabus for the entire topic of infinite series. So thank you very much for your patient hearing.